All right, welcome to The Explainer. Today, we're going to break down a core concept in statistics that, honestly, you use every single day, probably without even thinking about it: counting. Now, I know it sounds super basic, right? But mastering it is the secret to understanding the odds of, well, pretty much everything.
I mean, have you ever wondered how you'd actually calculate the odds of cracking a password, or picking the winning horses in a race, or the big one, hitting the lottery jackpot? It all starts with one thing: knowing how to count every single possibility. And today, we're going to walk through the 5 key methods to do just that.
So, here's our game plan. We'll kick things off with the most basic rules and then build our way up to the more complex stuff. By the end of this, you're going to have a complete toolkit for counting just about anything.
Okay, let's dive right in. Our first tool is called the multiplication rule. This one is super intuitive, and honestly, it's the foundation for everything else we're going to talk about today.
The rule is really simple. If you have a series of choices to make, one after the other, you just multiply the number of options you have at each step. That's it. That gives you the total number of possible outcomes.
Let's make this real. Imagine a hacker figures out a password is exactly 5 characters long. Now, if you think about a standard keyboard, you've got uppercase letters, lowercase letters, numbers, symbols. That's 92 different options for each and every character. The key here is that the choice for the first character has nothing to do with the choice for the second, and so on. They're independent.
So what do? You multiply 92 by itself 5 times, and what you get is staggering: over 6.5 billion possible passwords. The big takeaway? This is why password length is so important. Just adding one more character makes the number explode, making it way harder for anyone to guess.
All right, next up, we have a really powerful shortcut called the factorial rule. This is your go-to whenever you need to figure out how many different ways you can arrange a whole set of unique items. That little exclamation mark you see? That's a factorial. It's just math shorthand for taking a number and multiplying it by every whole number below it, all the way down to 1. So if you have n things, there are n factorial ways to line them up.
Let's visualize this. Take the word Steam. It has 5 unique letters. For the first spot in a new arrangement, you have 5 choices, right? S, T, E, A, or M. Once you pick one, you've only got 4 letters left for the second spot, then 3 for the next, and so on, until you're left with just one final letter for the last spot. So you just multiply those choices: 5 times 4 times 3 times 2 times 1. That's 5 factorial, which equals 120. So there are 120 different unique ways to arrange the letters in the word Steam. Pretty cool, huh? Okay, that's great for arranging all the items. But what happens when you're not arranging everything? What if you're just picking a smaller group out of a larger set, and the order you pick them in is absolutely critical? Well, that's where permutations come into play.
And this is the formula for it. Don't let it look scary. It helps us count ordered arrangements, like who gets gold, silver, and bronze. N is just the total number of things you have to choose from, and R is how many you're actually picking and arranging.
A perfect example of this is a trifecta bet in a horse race. Let's say there are 20 horses running. That's our N. You're trying to pick the top 3 finishers in the exact order they cross the finish line. So R is 3. Here, the order, first, second, third, is everything. If you get the horses right but the order wrong, you lose.
So when you plug those numbers into our permutation formula, you find out there are 6,840 different possible trifecta outcomes. That means if you just randomly pick 3 horses, your odds of winning are only 1 in 6,840. But, life isn't always so neat. What if some of the items you're trying to arrange aren't unique? What if some are identical? Well, there's a tweaked version of the rule for that. You just have to divide out the arrangements of the identical items. For example, think about designing a survey. Let's say you have 10 questions, but 2 of them are identical, and another 3 are also identical. The number of unique ways you can order that survey drops from over 3 million all the way down to about 300,000. It shows you why it's basically impossible for pollsters to test every single version of a survey.
Okay, so far, order has been king. Permutations, factorials, it's all been about the sequence. But now for the big question: what happens when the order is completely, totally irrelevant? This brings us to our next tool and probably the most important distinction we'll make today: combinations.
And this is the crucial difference. For permutations, the sequence matters. ABC is a different outcome than CBA. Think of it like a list. But for combinations, the sequence doesn't matter.
A group with A, B, and C is the exact same group, no matter how you write it down. Think of it like a group.
Now, if you're worried about mixing these up, here are a couple of handy tricks to remember them. For permutations, think position. The position of each item is key. For combinations, think committee. If you rearrange the members of a committee, it's still the exact same committee, right?
And here's the formula for combinations. Now, look closely. See that extra r factorial on the bottom? That's the only difference from the permutation formula. And that little piece is the magic ingredient. It's what mathematically divides out all of the duplicate arrangements to give you just the number of unique groups.
And the classic go-to example for combinations is, of course, the lottery. You need to pick 5 numbers from a pool of 35. It doesn't matter one bit if the machine draws your numbers as 5, 10, 15 or 15, 10, 5. As long as you have that group of numbers on your ticket, you win.
When we run those numbers through our combination formula, it tells us there are 324,632 possible tickets. Your probability of winning with a single ticket is tiny, which is why the source material we're looking at cheekily calls the lottery a tax on people who are bad at math. Kind of makes you think, doesn't it?
Okay, let's do a super quick recap. Think of this table as your decision-making guide. To pick the right tool from the toolkit we just built, you just need to ask yourself one simple question. Does order matter? If it does, you're looking at a multiplication, factorial, or permutation problem. If order doesn't matter, you know it's a combination. Simple as that.
From the cards in your hand during a poker game to the way data is encrypted in computer science, these fundamental rules are working behind the scenes, governing the probabilities all around us. You now have the framework to actually analyze them. So the only question left is, what are you going to explore first?